Hello everyone. Today we're going to talk about Project 2. The official name is The Walking Deadline. What I could fit in my notes here below my name is the Zombie Apocalypse, or sometimes we just call it the Zombie Project. Now this project, unlike Part 1, is broken down into two distinct parts. Part A is the zombies. Part B is implementing priority queues. Part A is very specific and stuff about zombies. Part B is very generic and has nothing necessarily to do with zombies. And in Part A, we're going to be using priority_queue. In Part B, we're going to be implementing different ways that a priority queue could be created. Now, you will see on the AutoGrader there are two different projects that you can submit to. Part A, Zombie Apocalypse. Part B, the priority queues. You get 2 submits per day per part. And if you use your submits for Part A, you still have your submits for Part B. If you don't use your Part B submits today, then you have basically wasted those. In Part A, once you find enough bugs, you can earn an extra submit per day. And if you want to know that number, look at the scoring student test files for Part A. Will show you the total number of bugs, how many bugs you have to find to start earning points, how many for full points, and how many will get you that extra submit per day. Also, if this becomes the case and later on in the project you decide, I'm going to have to use a late day to finish this. If you tell the AutoGrader to use a late day on either part, it will automatically extend 1 day for both parts. Now, before we talk about either Part A or Part B, what we want to do is we want to talk about functors in general, because we're going to have to use functors in both parts. In Part A, we're going to be using priority_queue from the STL, and in Part B, we're going to be implementing different ways of creating a valid priority queue. Now, we need to talk about functors because if we put anything more complicated than like an integer or a string inside of a priority queue, we're going to need a functor to determine priority. So, the key is, and this is true for either part, when we have a functor for a priority queue, it always has to answer the same question. So let's say I have 2 parameters. We'll call them A and B, lowercase a and b. Now, the functors for a priority queue will always get 2 parameters. What will their type be? It should be whatever's in the priority queue. So if you had a priority queue of zombie objects, the parameters would be 2 zombie objects, which I'd better pass by const reference so I don't copy them. If your priority queue contains zombie pointers, then your functor would accept 2 zombie pointers. So whatever the type of the priority queue is, will be the types of the 2 parameters to the functor. The functor always has to answer the same question. It has to answer the question, is the priority of A less than the priority of B? And if the functor says true, what that means is that A has a lower priority and B should be closer to the top of the priority queue. It should have the higher priority. So you always answer this question. How you answer it might depend on whether you want the smallest value to be the highest priority or the largest value to be the highest priority. Often to get this correct, what I'll do is in my head is I'll write down, I'll say like, okay, if A had this data and B had that data, what should the answer be? Should the answer be true or false? Is the priority of A less than the priority of B? So I figure out my example, I figure out my answer, is the priority of A less than B true or false? And then I figure out the code to make that happen. And that's the easiest way to keep it straight in your mind, is write down the question, remember what the question is, and then make some data that will force you to get the answer right. Now, when we code part A, our functor will be sort of the outside view. This is, I am using priority underscore Q. So in part A, we're going to be using priority underscore Q of blah, blah, blah functor. And we have to give it the functor so that it will get things in the right order. We have sort of the outside view. I don't care how priority underscore Q works under the hood. I apparently have a starving cat. Sorry. So we don't care how it works under the hood. We just have to make the correct functor so that priority Q can do its job and make sure that when the priority of A is less than the priority of B, it makes sure that that object B is closer to the top of the priority queue. In part B, we're going to have the inside view. So inside of the implementation, I've got to say things like, and I'll give you a really specific example, I've got to say things like, if this arrow compare of something, comma something. Okay, parentheses, parentheses. And so if it says true, if that call to this compare is true, that means that this thing A has a lower priority than that thing B, and depending on which priority queue I'm implementing, I'd have different code to ensure that A ends up lower and B ends up higher. So we'll talk about part B a little bit more later and what this compare and stuff like that means. Okay, so let's talk about part A first. I wanted to do sort of the general stuff, and then we'll talk about part A now. So part A, first tip on part A is, although there are three. So there's verbose mode, there's median mode, and statistics mode. The verbose mode, you want to get it working along with your project because it's really easy. It's basically going to be a couple of ifs. If verbose mode is on, then I do this printing. And you want to do that up front because if you don't have verbose mode on and all you get is an answer, like defeat in round 5, and you're like, wait a minute, I was supposed to win. How could I have a defeat when I'm supposed to get a victory? Without verbose mode, it's impossible to tell what went wrong. Verbose mode will tell you what zombies got generated, etc., and that will help you get things correct. Okay, we'll talk about the other flags later on. But the verbose mode, I wanted to point out that that's really critical. As you start working on part A, do verbose mode, which means that we kind of need to do the command line processing first. That's not too bad. It's going to be a lot like Project 1. We've got 3 different command line flags, verbose, median, and statistics. And just a quick overview, verbose and median appear by themselves. They have no argument. Statistics has a number after it. It has a required argument. Okay, so then, next thing is reading input. When you're reading input and you're working on the round breakdown section of the project spec, you have to remember that every round has to run. Like if zombies exist, they have to move forward, the player gets to shoot them, etc. I forget the exact order of everything. That's why we've got a numbered list. So that's true. Every round has to run, but not every round has input. I could have an input file that has a round 1 and produces a bunch of zombies, and I'm shooting them in round 2, 3, 4, but no new zombies are appearing, and then all of a sudden new zombies appear in round 5. So you've got to be careful when you read. You really need to keep track of 2 separate numbers. The what round am I on right now? So we could think of that as so this is part A. We could think of it as the current round, and a separate variable might be the next round in the file. So what is the next round in the file? And you've got to make sure that you don't read too far ahead. Like, I don't want to read all of the stuff that's going to happen in round 5 when I'm in round 2. I just want to read enough to know what's going to happen next. So when you start reading, and you have to read, there's some stuff up at the top, the header stuff, that'll always be there. That'll describe, there'll always be one comment. You don't have to worry about what if there's 1, what if there's 7, what if there's 0. You've already handled that in Project 1. So in Project 2, there will always be one comment line. You can just get line it, throw it away. There's a couple of fixed lines after that describe certain things about the simulation that we're running. And then there will always be at least one round of input. We guarantee that. So you know up front you can read the dash 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 line. That's the line of dashes that comes between each round. So you know you can always read that. You know you can always read the round colon space number. You know you can always read that. And then decide whether or not it's time to read more. One thing you can also do, when you try to read the dash dash dash, one thing you can check is you can do if cin.fail, parentheses, or equivalently, you could say if not cin. Those are equivalent. Both of those say the last operation failed. So after you try to read the line of dashes with like a greater than, or a get line, you can check if cin is in a failure mode, or if not cin means, hey, that reading that line of dashes failed. That means there's no more rounds to read. But it doesn't mean the simulation's over. I could have just finished reading around with 1,000 zombies and they're coming to eat my brains. I've got to keep the simulation running until either I'm dead. Okay, simulation ends when I'm dead, almost. Just check the round breakdown for that. So when I die, the simulation is going to end soon after that. And if there are no more zombies left, and there are no more zombies left in the file. So when I say no more zombies left, I mean basically if the priority queue is empty and there's not going to be any future rounds, then you know that the simulation is going to come to an end. But the priority queue being empty does not mean you're done. This is not like Project 1 in that regard. Okay, so when we start creating zombies, one of the things is that zombies have a couple pieces of data with them, and they're going to have to go into a priority queue. So you must have some data structures in the project, as in like a struct or class. At the very least, you're going to need a struct or a class to hold a zombie. You're going to need a struct or a class to be a functor. You cannot get this project done without it. So then we put zombies together in this struct or class, and then, we're going to have to put them somewhere. Now, one of the things that will happen is you'll see that we have to keep track of, potentially, depending on what command line flags are on, we might have to keep track of zombies in different places. Like I might have to keep track of the zombies that are active versus the ones that are dead. I've got to keep track of who's in the priority queue. And we don't want to make lots of duplicates of zombies because the zombie object is going to have a string and a couple integers. And if I start making copies of zombie names and a bunch of integers that go with every zombie, if I keep making copies of them, two bad things happen. One is I start wasting memory. And another thing that happens is I can't tell what's happened. So think about this. I've got somebody in the priority queue. I know the top of the zombie priority queue. I know it's been shot. I know it's taken damage. I know that zombie has or has not been killed yet. But where is that zombie in my other container of like the zombies? So you have to think of this project as having like a master list of zombies. Zombies go into the master list, and then something goes into the priority queue. So if we don't want to put copies of zombies, because that would waste memory, then we might put what in our priority queue? If we don't want to copy the zombies, we could put pointers to zombies. Now we have to be careful here. If we say, ooh, I know what I'll do. I'll make a vector of zombie objects. So I'll make a vector of zombie objects. And I'll call this like my MZ, my master zombies. Okay, so I've got my master zombies, and I push a few into there, and then I figure out their pointers, and I put their pointers into the priority queue. Okay, great. Until more zombies appear. When more zombies appear, then my vector has to grow. If my vector has to grow, think about what happens behind the scenes with a vector of objects and a growth and what happens when pushback needs more room. So it can be dangerous to make a vector of zombies and take pointers into the vector and put those in the priority queue. So we have to either find a different container that doesn't invalidate things when it grows, or we'd have to do everything on the heap. And those are both valid ways to do it. Both of them can get you all the points. You just have to pick a method and stick with it. Okay, so we've got to put things into our priority underscore queue. Now, declaring a priority underscore queue is a little bit tricky, not terrible. But when we just declare a priority queue, we say priority underscore queue of a single thing like int. Let's call it PQI. And that one works by defaulting everything else other than the integers. And that will produce what's called a max heap. What this means is that the highest value is the highest priority. Priority queue, the highest priority is always on top. Max heap is a shorthand way of saying the maximum value is the highest priority. And if I said min heap, I would mean the minimum value is the highest priority. So by default, we get a max heap of integers. But here I'm going to have to put zombie somethings in there. So what I need to do is I need to say priority underscore queue. Oops, queue, can't write. Angle brackets. I've got to have a type, some type, comma, let's call this x. Whatever x is, you'll then say vector of x, and then you'll say like functor of x. And these are all types. These are not objects of types. And we could call this like PQX. So if you have to overload the functor, you have to specify this is not saying what the external container is. This is saying, hey, priority underscore queue, you should put your internal data in a vector. And this can be different from your master list of zombies. Generally, because vector of whatever type is the default, like when we did this, it defaulted to a vector of integers. So because the STL people, I assume, know best, because they said make the default type a vector of whatever the first thing is, I like to go with their feelings. So since they say vector of x, I say vector of x. So whatever type x is, whether it's zombie objects, zombie pointers, whatever, vector of same thing, followed by our functor type that we talked about earlier. So functor type is going to be a class or structure. It's got to have an overloaded operator parentheses. It's got to accept two things of type X and do so efficiently. And it's got to answer that question. Is the priority of A less than the priority of B? Now, when we talk about making that functor, so inside of the function, we've got to answer that question. And so the priority is first based on ETA. The zombie that has a lower ETA, estimated time of arrival, has a higher priority. So basically what I'm saying is I shoot the things not necessarily closest to me, but the ones that are going to reach me the soonest. So let's just do a quick little example. If I had a zombie, I've got a distance, and a speed, and a distance, and a speed. Okay, so I've got one at a distance of like 4 with a speed of 1, and I've got one at a distance of 10 with a speed of, let's say, 5. So this one has an ETA of 4. This one has an ETA of 2. Now I did it here with integers. That comes out. The spec will tell you just divide integers by integers and use the integer. So here I would say, hey, this one has to have the highest priority. This one is more important because although it's further away, it's going to reach me sooner. So that's how we prioritize. So we pick the lowest ETA comes first. If those are the same, let's say I had 2 and 1, then I've got a 2 and a 2. Then we have to go to the tiebreaker, which is health. Health and health. Okay, so say these were health 5 and health 2. This one still has a higher priority because they're both going to reach me about the same time, but I've got a better shot at killing the one with less health first. So I'm hoping that, hey, if I kill that one first, then maybe I'll still get a chance to kill the other one. So maybe, maybe not. We'd have to run it and see. Now, what if the health is the same? There's another tiebreaker. We break their name. The name that is closest to the beginning of the alphabet is the higher priority. So like the example in the spec, I think, says if we had Paoletti and Darden and they were both all lowercase, then Darden would have the higher priority because it has the lower name. So get closer to the beginning of the alphabet. So that's how you have to break ties inside of your functor. So your functor's got to do those comparisons. Then, okay, so that takes care of most of the zombie stuff that's not in the spec. So then the median mode. So let's talk about the other flags. So median mode, the idea here is that during each round, we're going to print out some statistics about the median information about different zombies. So to do that efficiently, we need a good data structure for that. And there is a separate video. I'll link it below in the description for this one. It's already recorded as sort of a generic how to do a fast running median. And it's been created for a previous semester, completely different project too, I'm pretty sure, but same idea for how to efficiently keep a running median. And the last one is the statistics mode. So statistics will always have a number after it, and we guarantee the number is always going to be at least 1, and there will always be a number there on the command line, so you don't have to worry about that stuff. So if statistics is on the command line, there will always be something after it. It'll always be an integer. It'll always be greater than 0. Did I say greater than 0? It'll always be greater than 0. Statistics will always be at least 1. So then for statistics, it says we've got to print out the first and the last, something about the first and last, and the most and least active. So the first and last are actually the first and last killed. So we've got to somehow keep track of first and last killed, and we've got to keep track of most and least active. Now, for first and last killed, that's pretty easy. We're going to need a separate container, but we're going to need a separate container separate from our master zombie list. Oh, that reminds me, master zombie list. Linked lists are never your friend. in 281. They use so much memory, they're not very efficient. So linked list is not the answer for the master zombie list. We may say list, but it doesn't imply linked list behind the scenes. So for the first and last killed, we need some sort of container of what order zombies were killed in. For the most and least active, my hint is remember what this project is all about and think about constructors. They are important for doing that the most efficient way. And think about this. Another way to think about this, if you're being efficient or not, is think about what if there was like, so I've got like dash S, let's say 5,000. Okay. Well, first of all, let's stop worrying about efficient first. What if the actual number killed was 100? Well, then I can only give the first 100 and last 100. I can only give and if there was only, let's say that there was a number created was 200. Well, then most and least active, there could only be 200 in that. So you first got to limit your output by basically the smallest value that can be done. Now, let's think about, so if I have statistics 5,000, what if the number, and this is most and least active would be the number created. So what if there was 200 that were created? And I'm asking for stats on 5,000. I've still got to be efficient about it. Also think of it the other way. What if there was 2 million created and I have to do statistics on 5,000? Would I still be reasonably efficient? What if it was dash S 2 million? So think about these different situations and come up with sort of the best idea that covers all of them. And like I said, remember what this project is about and think about constructors. Okay, last thing we want to talk about is when we're coding inside of Part B. Now, there is a separate video for Part B. I'm going to link that in the description down below also. And Part B is very generic. We're just going to be implementing a couple different priority queues, and we have to do things properly. We have to think about, hey, I'm inside the priority queue. I've got to make sure that I give things in the correct priority. When people ask me who's the top, I have to show them the right one. When they say pop off the highest priority, I've got to get rid of it. I've got to do that as efficiently as I can for this particular type. Okay, so make sure that you watch the other videos also, and a little bit of advice for working on this project. So the last thing is working on this project. My suggestion is, don't try to do all of Part A before you start thinking about Part B, or vice versa. Watch out, and there's a warning about this in the project spec. The pairing heap is not an easy data structure to implement. You should plan on a couple days of just reading about pairing heap, thinking about it, watching the video again, coding it, watching it crash, debugging it, optimizing it, etc. So a couple days just for pairing heap. So my suggestion is start making some progress on Part A. Start looking at the zombies and the command line and starting to read input and starting to create your data structures. But at the same time, start looking at what we already gave you for Part B. Start thinking about implementing in order. So Part B in order. Sorted is fairly easy. Sorted, we're talking, I know it's single-digit number of lines of code. Sorted priority queue is all about using the STL to do your work for you. If you find yourself writing a loop, no, make the STL do that. And I'm not saying like, oh, I'll use a range-based for loop. No, you don't want to use much in the way of loops at all. You want to call something in the STL to do it for you. So in sorted, we're going to use a vector of data. It's required. There's a data vector already already created for you that you must use. So you use that data factor and you use other parts of the STL to make that happen. Part B is going to be lecture on the topic of, it's called heaps and heap sort. So the heaps and heap sort lecture will give you everything you need for the what's called the binary PQ. And then the pairing PQ is, we've given you 2 papers about it, 2 PDF files. We've given you a video about it, and if you still have questions, be willing to come to office hours with them. And also remember, come to Proffice Hours, to our one-on-many meet, and even if you don't have questions, come and listen to other people's questions. You will find that other people have similar questions that you have. You'll find that other people ask questions that you didn't even know you wondered about yet, and it'll really be a big help to you. Okay, so good luck on the project. Don't stress your brains too much and make sure you don't get the meeting.